Hello viewers, welcome back to my channel. If you are new to this channel, you are welcome. Click on the subscription bell and turn on the notification button so that you can be informed whenever a new video is released. For our old subscribers, thank you for staying tuned. Today, we are going to be looking at mechanics, and the topic of discussion is moment of inertia. Moment of inertia. What do we mean by moment of inertia? The moment of inertia of a body is simply the measure of the resistance that body offers to rotation. The measures of the resistance that body offers to rotation. How that body is trying to resist rotation. That is what moment of inertia is all about. For us to understand this better, we say that the moment of inertia of an object or of a body, this is the measure, of the resistance a rigid body. The measure of the resistance a rigid body offers to rotation. So the measure of the resistance a rigid body offers to rotation is called moment of inertia. And it is denoted by symbol R. Please, let's take note of that. The moment of inertia is denoted by symbol R. Okay, so let's consider a point mass system. Let's consider a what? A point mass system, that is a mass that is attached. A mass that is attached to a spring. We want to consider a mass that is attached to a spring, and that mass is pinned or rotated about its axis. Attached to a spring which is rotated about an axis at a fixed point. Let's look at this. So this is my mass M. The mass is rotated at this fixed point. So this broken line here is showing the point of rotation. This is very important in solving any questions related to moment of inertia. They must always tell us the axis of rotation. Either it is rotated at where? At the end point, or maybe at the middle. But in this case, we are considering what? A mass that is attached to a spring or a rope and is rotated about what? An axis at the fixed point. So this shows the axis of rotation. We notice that from that axis of rotation to that mass, it covers a given what? Distance. So let's call that distance R. It covers what? A given distance. So I'm using R to denote that distance. So in the real sense, it simply means that for me to calculate the moment of inertia I, it is simply the product of the mass and the distance it covers from the point of rotation. The product of the mass and the distance it covers from the point or the axis of rotation, and multiplying the what? R squared. So this denotes the formula for calculating moment of what? Inertia. Of what? Of a mass that is attached to a spring. Please take note. The simplest formula for moment of inertia of a mass that is attached to a spring or a rope is given as I equals mr squared, where m is the mass of that object that is measured in kilogram and r is the distance of that object from the point of rotation. The distance of that object from the axis of rotation. So I equals mr squared. This is the formula that relates what the moment of inertia to the distance of rotation. Okay. What of, let's consider a discrete system of particles. That is, we know their number. We know their what number. Considering a discrete this system of what particle, how do we calculate the moment of inertia of a discrete system of particle? That is, for instance, a system that contains maybe 2 masses, 3 masses, 4 masses, 5 masses. How do we calculate the moment of what inertia? In that case, for us to calculate the moment of inertia, it simply means that what we are calculating the moment of inertia of the individual masses from their axis of rotation. That is for discrete system of particle. That is for discrete system of particle. For discrete system of particle, our moment of inertia I is given as summation from I equals 1 to what n of I multiplying what of m multiplying what r squared. For instance, if I want to find the moment of inertia of, let's say what, of a particle that contains what 3 masses, that is the first mass I call it m1, the second mass I call it m2, and the third mass I call it what m3. Because it contains 3 masses, I'm going to have the moment of inertia to be equal to, for the first one, m1 r1 squared plus, for the second one, m2 r2 squared plus the third one, m3 r3 squared. So this is the moment of inertia of what? Of 3 masses. Of what? 3 masses. The m are what? M1, M2, M3 are what? Are the masses. And R1 is the distance of the mass M1 from its axis of rotation. R2 is simply the distance of mass M2 from its own axis of rotation. Similarly, M3 is also what? The distance of this mass from its axis of rotation. So this is how we calculate the moment of inertia of a discrete system of particles. This is how we calculate the moment of inertia of a discrete system of particles. So let's look at this example. Obtain the moment of inertia of the following systems. Obtain the moment of inertia of the following systems. Look at it. The first one, we have mass 2 kg, the second mass 3 kg, and the third mass 5 kg. So this shows the what? Axis of rotation. In this system, you can see, as you can see the broken line, it shows that it was rotated at the middle. It was rotated that way at the midpoint. Okay? For us to calculate the moment of inertia, don't forget, since we also have what? 3 masses, even though we have more than 3 masses, this is how we evaluate them. For us to calculate the moment of inertia, we are using what? I equals what? M r squared. Summation of what? M r squared. The summation of m r squared. That is, for the first one, the m1 with what? r1 squared plus m2 r2 squared plus m3 r3 squared. Because I'm having what? 3 different what? Masses. If I'm having 4, I will add the what? Fourth one. Since I know my axis of rotation, the axis of rotation here is at the center or at the what? At the midpoint. So for the first one, our moment of inertia is going to be the first mass, which is what? 2 kg, multiplying the distance from that mass to the point of rotation. The distance of that mass to the axis of what? Rotation. That distance is 1.5 meters. It was rotated at the what? At the middle. So that means 2 multiplied by what? 1.5 all squared plus the second one. The second mass is what? 3 kg. What of its own distance to the axis of rotation? It has no distance. So I can put what? 0 squared plus the third one, M3, which is what? 5 kg multiplied by what of its own distance from the point of rotation? It was rotated at what? At the middle. And the distance it's covered is what? 1.5 meters. 1.5 meters. So when we what? Evaluate this will give us the first one we have 4.5 plus the second one we have 0 plus the last one we are going to have 11.25. So when we add 11.25 to 4.5, so our result for this moment of inertia of this object is 15.75. Out of the unit is what? Kilogram, then meter square. Kilogram, meter square, 15.75 kilogram, meter square. So this is how we calculate the moment of what? Inertia of a given system. Because since this is a spring, you can see they are like what? Springs, they are attached. That is why we use the formula NR squared. Please, we don't always use this formula. It depends on the type of material that is given to us. Since this is what? Ordinary spring, just like a rope. Since this is ordinary string, we can use this what? Formula, because it is what? Ordinary string. Okay, so look at this next example. Example 2. We want to obtain the moment of inertia of this system. You can see here, I'm having what? 4 different masses. Then you notice that the axis of rotation is what? At one of its ends. So please always take note of this. Always take note of your point of rotation. It's very important in solving questions on moment of inertia. So in solving this, I'm having that what? My moment of inertia for this system, I'm having 4 masses. The first one, M1 R1 squared plus M2 R2 squared plus M3 R3 squared plus M4 R4 squared. M4 R4 squared. Okay? So let's start. For the first mass is what? 1 kg. Multiplying the distance of that 1 kg from the axis of rotation, that gives what? 0 squared. Why? It is rotated at where? At the end. It has no distance from the point of rotation. Plus the second one. Our second mass is what? 2 kg. Multiplying what of its own distance from the point of rotation. Its own distance from the point of rotation is 2 meters. So we are having 2 squared. Plus the third mass, we have 3 kg. What of that third mass, its own distance from where? From the point of rotation. The distance of this mass 3 kg from the point of rotation is from this point to this point. It was rotated at where? At the end point. So the total distance is this distance plus this distance. So at the end of the day, when you add this and this, I'm going to have what? 3 squared. That is its own distance from where? From the point of rotation. We are always interested in the distance from the point of rotation. Okay? Plus the last one, which is what? Mass 4 kg. What of its own distance from the point of rotation? It is from this point to this point. This 2 plus 1, that's 3. 3 plus 1.5, this gives us what? 4.5 squared. 4.5 squared. So when we solve this, we are going to have the first one is 0 plus the second one 4 times 2 gives 8, plus the third one, 9 times 3 gives 27, plus the fourth one. The fourth one we are having 4.5 squared, multiplying 4. This will give 81. So when we add 81 to 27 plus what? Plus 8. This gives us 116. 116 kilogram meter square. So this is how we evaluate the moment of inertia of this system that is rotated at the end point. So the next thing we are going to look at is the factors affecting the moment of inertia. What are the factors that affect the moment of inertia of a body? There are two major factors that affect the moment of inertia of a body. The first factor is the mass of that body, the mass of the body. And the second factor is the location of rotational axis. The location of rotational axis, that is the point at which those bodies are being rotated. The point at which those bodies are being rotated. These are the two factors that affect the moment of inertia. So, for continuous distribution of particle, we can see that we have different examples here, different systems with their moment of inertia. For the first one, in the case of uniform rod, when the system is a uniform rod, what happens to the moment of inertia? Let's look at this. For uniform rod, you can see when the axis is at the center, when the axis is rotated at the center, the moment of inertia I equals 1/12 ml squared. But when the axis is rotated at the end, our moment of inertia is 1/3 ml squared. Don't forget, m is the mass, where l is the length of that rod. Number 2, for circular ring. Let's see what happens in the case of what? Circular ring. You can see that when the axis is rotated at the center, our moment of inertia still remains mr squared. But when the axis is rotated at the diameter, our moment of inertia becomes 1/2 mr squared. Similarly, for circular disc, our moment of inertia becomes 1/2 mr squared. Similarly, number 4, for a sphere, when the system we are talking about is in the form of what? Of a sphere. For a solid sphere, if we are talking about a solid sphere, our moment of inertia, the formula becomes 2/5 mr squared. If it is a thin sphere, our moment of inertia becomes 2/3 mr squared. Also, number 5, for a cylinder, if the system we are considering is in the form of a cylinder, if the cylinder is a solid type, that is a solid cylinder, our moment of inertia becomes 1/2 mr squared. If it is a thin cylinder, our moment of inertia becomes mr squared. And if it is an annular cylinder, our moment of inertia becomes 1/2 m into r1 squared plus r2 squared. And the last, if the system we are interested in is a slab, we know what we mean by a slab. Our moment of inertia is given as 1/12 m into a squared plus b squared. So these are the moment of inertia for different systems. It now depends on the question that will now determine the type of formula to use. Don't forget, these are the different systems with their corresponding formula for calculating the moment of inertia. Okay, so let's quickly look at this example. Determine the moment of inertia of a uniform rod of mass 5 kg and length 80 centimeters. When rotated at the first one, its midpoint, the second one of its end. So we want to look at this question in two different perspectives. The first perspective is when it is rotated at the midpoint, what happens to the moment of inertia? And in the second perspective, we want to see when it is rotated at one of its ends, what also happens to the moment of inertia? Solution. So the first thing to do is to write out our parameters. What are the parameters given to us? We are given the mass to be what? 5 kg. What are we given again? We are given the length to be what? 80 centimeters. So meter, divide 80 by 100. When you divide 80 by 100, you are going to have 0.8 meters. Also, yes, you are given the what? The mass, and you are also given the what? The length. So I want to find the moment of inertia for the first one when it is rotated at the midpoint. For what? A uniform rod. Now, let's go back to our table. What is the formula for calculating the moment of inertia of a uniform rod when it is rotated at its midpoint? If you go back to the table, you are going to see that the formula is 1 over 12 ml squared when it is rotated at the midpoint. 1 over 12 ml squared, where m is the mass of that object and l is the length of that rod. Okay, so if I apply this, I'm going to have 1 over 12 multiplying the mass, which is what? 5, multiplying the mass is 5, multiplying the length, which is what? 0.8 squared. So if I apply this, I'm going to have my moment of inertia to be, so this will give me 0.8 squared multiplied by 5 and divide that result by 12. This will give me 0.27. 0.27 kilogram meter square. So that is the moment of inertia of that rod when it is rotated at its midpoint. When it is rotated at its midpoint. For the second one, we want to calculate the moment of inertia when it is rotated at one of its ends. When it is rotated at one of its ends, what happens to the moment of inertia? The moment of inertia becomes 1 over 3 ml squared. I equals 1 over 3 ml squared when it is rotated at one of its ends. That is 1 over 3 times the mass, which is still what? The same mass, 5, times the L squared, which is what? 0.8 squared. So this will give us 0.8 squared multiplied by 5 and divide that result by 3. This will give us 1.07. 1.07 kilogram meter squared. So this is how we calculate the moment of inertia of that rod, both when it is calculated at its midpoint and also when it is calculated at one of its ends.